Okay, 2 o'clock. Welcome in everybody to ME2001, also known as your favorite class. Yes. Today, we're just going to be reviewing for exam number 1. I posted a new set of lecture notes, which are kind of like exam review lecture notes. It's under kind of like the exam tab of Canvas. So if you want to kind of follow along with those, go ahead and do that. So we'll do that for a little bit today. Probably won't go the whole time today, maybe only a half hour or so today. And I want to give you enough time or kind of let you go a little bit early so that you can study for exam number 1. So exam number 1 is in class tomorrow. The instructions for taking the exam are on Canvas. So if you'd like to sort of look at that, go ahead and do that if you need a refresher. The exam will be held virtually, so just come to the Teams meeting a couple minutes early, set up your pens and papers in front of you, then I'll release the exam at 2 and you can execute. All right. We'll have an exam review session tonight at 7 p.m. That'll be optional. I'm just going to be going over a couple of the practice problems from the exam review practice problems that I sent out. So as a reminder, there are these practice problems that exist also in Canvas under the exams tab. A lot of people were asking me for practice problems, so I've tried to provide some extra ones for you. And I've also provided my full handwritten solution for each of those problems if you'd like to try to sort of follow along with those. So plenty of stuff to do to keep yourself busy while you study and etc. All right. So any questions from any persons? Okay. Well, if there are no questions, let's do some statics. And today we're just going to do a review. So we've kind of taken it pretty slow in this class so far. We don't have a ton of material at this point, but enough where we can probably build some sort of review and have a nice exam before our break here. So today's lecture is exam 1 review. All right. And the exam is going to cover lectures 1 through 4. So lecture 1 was the introduction to mechanics. Lecture 2 is vector math. Lecture 3 is 2D particle equilibrium, and lecture 4 is 3D vectors and particle equilibrium. So those are your 4 topics. Not a ton from lecture 1. It was just kind of like an introductory rah, let's do statics lecture. So not a ton from that, but the other 3 lectures you should be ready for those. All right. So we've kind of come a long way. I think at the beginning of the class we were doing a lot of stuff that you'd probably seen in other classes like vector math. And then we eventually get to a point where we're doing 3D vectors and 3D particle equilibrium, which probably stuff you've never done before. So let us do some review. And the first thing we're going to do is start with vectors and vector addition. And specifically vector math. Okay, so at the very onset of this class, I introduced this class by saying that we're going to talk about force vectors and how forces act on objects that are not moving. That's why this class is called statics. And so we, from the very get-go, sort of defined what a vector was. So a vector is a mathematical expression that has both magnitude and direction. Okay. For addition, we follow the parallelogram law for vector addition, which basically means that we can take these vectors, and if we want to add them together, you put them like tip to tail, and that can give you some sort of addition. So addition follows parallelogram law. Addition is cumulative and associative. Okay, so what do we mean by all these things? Well, if we have some vector that exists out in space, some point that exists out in space, it's got vectors here P and vectors Q. Then the addition of these two together can be done sort of with the parallelogram law, which is that we can put either one of these tip to tail in sort of either order. So adding Q to the tip of P, so something like this, or you can add P to the tip of Q. Either way, you're going to end up with the same general resultant for P plus Q, which is a vector that looks something like this. Okay, and this figure does a nice job showing that these things are, in fact, commutative. So the commutative property is something like P plus Q is equal to Q plus P. So there's your commutative property, and I think you can kind of see just from the image here of the drawing that that is true. You're going to end up with the same result in both situations. All right. We also did some things to show that it's associative. And that is something like P plus Q plus S is equal to P plus Q plus S, which is equal to P plus Q plus S if you have three vectors together. We had a nice picture, a drawing of your notes of this in the second lecture. I'll bring it in here just for clarity's sake. But you should have this kind of already in your notes from before. Picture that looks something like this. This is your associative property. The resultant of these three guys individually added together is the resultant of like those two guys added together plus this guy, which is the same as like these two guys added together plus this guy. Okay, so that's kind of the associative nature of these guys. Okay. We also called this like summation of all of these forces together. So something like this P plus Q plus S, the resultant force. And we generally labeled that as capital R, which equals the summation of some vectors that we have. Here I'll just say it's summation of some force vectors that we have, but generally it's a summation of all vectors. Or the resultant is like a summation of multiple vectors that are adding at a particular point. Right. So in this figure labeled above, you could think of like this P plus Q plus S. This could be a resultant vector R. All right. So at the very beginning of the class, when we were looking at doing some vector addition, we looked at sort of making triangles, using law of sines, using law of cosines to sort of like calculate what these general forces are and sort of using geometric relations between sort of the shapes that were formed with all these vectors to try to figure out like what the vectors' length and direction were. That was a little bit inefficient. So we introduced some tools that helped us sort of add vectors a little bit more appropriately at a particular point. And that general concept revolved around unit vectors and principal directions. So after we initially just talked about vector addition briefly, then we talked about unit vectors. And specifically, we talked about unit vectors and rectangular components. Okay. And just a reminder that unit vectors are vectors. Okay, so they have magnitude and direction with a magnitude of 1. Okay. And these are helpful because if we know some component of a force in a general direction, we can express that particular portion of the force using a unit vector. So for instance, if you know, let's say the component of a force along the x direction, you can represent that component of the force in vector form by saying the magnitude in the x direction of that force times I hat, which would be like a unit vector in the x direction. So for Cartesian or rectangular directions, we typically use I for the x direction, j for the y direction, and k for the z direction. So we're very used to this. We started kind of with planar 2D vectors, so we focused in and dialed in on I and j first, but eventually we added, the third dimension to that later. So I'll just kind of include it here now. And so that way, with arbitrary force in space, here's my force. If we slap some coordinate system on this guy, we can just generally use our traditional 2D coordinate system. X and Y. Then I could say that the component of this particular force in the X direction and the component of this force in the Y direction, let's call this Fx and Fy. I can say then that by our vector addition, this is Fx plus Fy. And if I happen to know the magnitudes of those general forces, force Fx and the magnitude of the force Fy, I could represent this as my vector F is the magnitude of the force in the X direction along that X direction, so I hat. So the magnitude of that force is whatever it is along the direction I hat, plus the magnitude of this force in Y along that particular direction, J hat. And if we happen to be working in 2D, and let's say we know what this angle here is, let's say we have that particular angle theta, or later we call this theta x. For now, I'll just call it theta. We can sort of use our trigonometric relationships to relate the magnitude of the force F to the magnitudes of the individual directions along X and along Y. So finally, we can represent this as something like the total magnitude of this force F resolved into the X direction with cosine of the angle theta plus this magnitude of the force, the total magnitude of the force resolved into the Y direction with the sine of the angle in J hat. So these are sort of some of the representations that we started with resolving a force into various directions using, let's say, this angle that we know between them, maybe the magnitude of the force and the general direction of the force, resolving it into its individual components and expressing it along those directions X and Y using unit vectors I and J. Very helpful and very useful. And the reason that it's helpful and the reason that it's useful is sort of the next step that we took in this particular class to get us to like a statics analysis was introducing the idea of 2D equilibrium and adding multiple forces at a particle together. So this is useful when we move to 2D particle equilibrium. And the idea generally here is that a particle is in equilibrium if the sum of the forces acting on that particle is equal to 0. All right. In 2D, we generally saw that the sum of the forces could be represented as the sum of the sort of forces in the X direction plus the forces in the Y direction, which was like the sum of the magnitude of force in X times the I hat plus magnitude of the force in y j hat all equal to 0. And we said that really the only way for this to generally be true, since this I and j direction are sort of mutually orthogonal and independent of each other, we said that the only way for this general expression to hold true is if each one of these individual directions has that general feel. So sum of the forces x equal to 0 and sum of the forces y equals 0, because they're sort of like mutually orthogonal or independent of each other. So both of these situations must be true. All of your force additions in the x direction and all of your force additions in the y direction must be equal to 0 for this general equilibrium to hold. And this is kind of like the foundation, these two equations here, of a lot of the analysis that we do in the beginning of this class, right? Looking at what is the equilibrium of this particular particle. If we sum all the forces in x, sum all the forces in y, and impose that the summation of those particular forces is 0, that allows us to sort of enforce what some of the tensions on a rope might be, for instance. And so we've done a lot of particular examples like that in class, and you should be ready to see some analysis like that on the test. Okay. So with this concept of equilibrium in mind, we then discussed or introduced what is a really foundational topic for this particular course, and that is the idea of space diagrams and free body diagrams. And because we have now this tool in our tool bag, this math tool bag that tells us if our particle's in equilibrium, all the sum of the forces is equal to 0, we now want to sort of be able to accurately analyze some sort of system that exists in the world and draw forces on that thing appropriately so that our onset, our initial drawing for our summation of our forces, once we go to the analysis, our initial drawing is correct. So this is one of the more important topics in this class, and we'll be doing a lot more of this once we get back from Christmas break, is looking at space and free body diagrams. Okay. So generally a space diagram is some sort of sketch or illustration or figure, or maybe just like a picture of real life. A real life picture could also be a space diagram. It's just some sort of representation of something that's happening in reality, all right? So a pictorial representation of a system of interest. Okay. And it is from those space diagrams that we usually construct free body diagrams. And a free body diagram is really the foundation of your engineering analysis. It's where you're putting all of the forces on a particular point or on a particular body, and that's going to be sort of the foundational point of your analysis. And if that's something you struggle with or have problems with, then it doesn't matter how good you are at math, if you can't set up the free body diagram correctly, you're going to have all sorts of errors, okay? So your free body diagram okay? This is a drawing of systems of forces acting on an object. Okay, and we usually make these by isolating a particular component and then drawing forces associated with all of the things that we like cut away from that particular body. So these are created by isolating a body or particle and including forces for all components isolated. Okay, so if I'm resting on a ground and I remove the ground from my space diagram, I'm maybe going to put some normal force that represents sort of the resistance that I had at the ground that's now stopping something from moving down. Or we've seen a lot of examples with like cables hoisting up a crate. You know, every time that you isolate a particular particle, if you're sort of isolating or cutting through a rope, you have to represent the force that's sort of acting through that rope appropriately and making sure that you're including that in your analysis. So I had this sort of series of images from the notes when we first discussed free body diagrams, and I particularly like this sort of set of images because it basically brings home everything that I want to sort of say about this. That's right. You've got some space diagram, some situation of real life that might be happening. These two guys that are hoisting a crate off the back of this truck, and you want to isolate or know some information about what's going on with these particular ropes. And so we can sort of isolate this point here at point A. And by isolating this point, we're sort of making a cut or cutting through three different points. We have this point here, and this point here that we're sort of cutting through. And every time that I'm sort of isolating or sort of cutting through one of these components, we see an associated force that pops up through cutting through each one of those guys when we move to our free body diagram. So we're just isolating that particular piece and accounting for all of the sort of components that we're removing or using to isolate point A. All right, so that's where we were with free body diagrams. So a lot of the homework problems that you've done so far sort of revolve around giving you a space diagram and then having you create the free body diagram and execute your analysis appropriately. So should expect some space diagrams that you have to convert to free body diagrams on the test. It's an important concept. All right. Now, once we've established and we did a lot of practice with free body diagrams in 2D, then we moved on to 3D vectors and 3D equilibrium. Okay, that's my volume here. And this is, I think, where things really start to get complicated in this class and maybe where we start to lose some people. Because 2D vectors, you've been doing 2D stuff pretty much your whole life since you were in, 6th grade and you made your first graph or something. I don't know. When do people make their first graphs these days? I don't know. Who knows? 3rd grade. I don't know. When do you make your first graph? Who knows? But I bet it was probably in 2 dimensions, that first graph that you made. So people are very comfortable, like, working in 3Ds or 2D or even working with vectors in 2D. Like, people seem to be very comfortable with that. But then once we teach you techniques of like moving to 3 dimensions and talking about unit vectors in 3D, that's when people start to get a little shaky and a little bit sort of confused and lost. And so the idea here is very much the same. In 2D, we've got some force vector that exists, and we're resolving that into X and Y components so that we can sort of describe its behavior and perform math on that vector in like the individual X space or individual Y space and do things accordingly. And the same idea holds in 3D. You've got some 3D vector, and now you want to resolve that vector into components that are in X, that are in Y, that are in Z, because you want to do math in that X, Y, Z space. And then once all is said and done, bring it all back together for additional information or presentation. All right. So we started just by introducing what's going on with 3D vectors. And maybe let's just draw one here and talk our way through some of the properties. All right. So here we have our typical sort of XYZ coordinate system. and we have some three-dimensional vector that exists in space out here. Let's just call it F. Now, just like we do in 2D, we can break this force down into its various components. And so let's say I have F that has sort of its tip of this particular vector hanging out over that particular spot. Well, we can break then this force vector down into components along X, Y, and Z. So here would be like my component in X. So here's F of X. This direction here would be the component of this force Z. And then up to this point would be my component of that force in Y. All right, so adding all three of those things together would give me my total force F, right? So here in 3D, this is kind of the foundation. My force is whatever we have in X plus whatever we have in Y plus whatever we have in Z. This is kind of going back to my original definition of vectors and vector addition, all right? We can interchange these things appropriately. And now the idea is I want to sort of represent the magnitudes of those forces using information that I might have about the problem. And generally the idea is that the force could be represented as the magnitude of that force along a unit vector associated with that particular force. So here we have a new unit vector we're introducing, and it's a unit vector we have called lambda. And there are many ways for us to sort of define this unit vector lambda and how to define sort of the magnitudes of the individual components of that force. And we sort of did this in two ways. All right. First was with directional cosines. And that is like given the angle between the force F and the axes X, Y, and Z. Those angles being theta X, theta Y, and theta Z. If you have those or somehow know those or could calculate those, then defining lambda is actually somewhat simplistic. It's just the cosine of those individual angles along those directions of interest. And that's probably like the easiest way to sort of define your unit vector. If you just happen to know the angle that the force makes with those various axes, then figure out what that angle is through geometry, or if it's given to you, just use it directly. And you could calculate what your unit vector is in the direction of the force. It's quite nice. So if we go back up to our image here and we wanted to sort of represent what that was, the angle here between F and the x-axis is theta x. The angle between my force and the y-axis, here is theta y. And the angle between the force and the z-axis would be theta z. So I think a couple of the review problems that you have, I think numbers 7 and 8, kind of work with this general principle, is sort of trying to figure out what those angles of theta are, and then using those to build a unit vector and work through your problem. All right, so probably the easiest method and most straightforward here. All right. The other way that we could define a unit vector is if we have a force directed between two different points, or a vector between two different points, where we happen to know what the distances are between the two different points in the various principal directions. Okay, so first here would sort of be with directional cosines, and second is a unit vector between 2 points. And so we had an image of this as well from our notes. I'll try to replicate that here. So here I have some point that exists in space, P1. Here I have some point that exists in space, P2. Let's say I have a vector that runs between those two guys. And let's call this vector F. All right. And let's say that there's some direction in X, Y, and Z that you have to sort of traverse to get from one point to the other. So we give our traditional labels, X, Y, and Z. And I would say here that there's a distance that exists between point 1 and point 2 that would be given here by these general vectors where they sort of represent distances in space. Or here, this would be the distance I travel in X. I typically call this dx, which would be the location of point number 2 in the X minus the location of point number 1 in X. So P1 at X1, Y1, Z1, and P2 at X2, Y2, Z2. Then my distance as X is X2 minus X1. My distance in Y is Y2 minus Y1. And then my distance in Z is Z2 minus Z1. All right. And if I have that information, I know what are those general distances between those 2 points. Then I can create for myself what is like a distance vector between P1 and P2. And so it's not necessarily the force vector. It is some other vector. It's like a distance vector. I think we called it like the vector capital A, capital B. And with that in mind, then, we could represent this distance vector AB as the distance in X, I hat, plus distance Y, J hat, plus distance Z, K hat. And if we happen to know that particular vector, we're able to define that particular vector, then if I took the magnitude of that vector and I sort of normalized that vector by its own magnitude, then I would have a vector of magnitude 1 pointing in that general direction. So what do I mean by that? I'm ultimately after what is this guy here, my lambda, which is a unit vector in the direction of that particular force. And I could define that using that distance vector AB. And to get a magnitude of 1, I need to normalize that vector by its magnitude, by the magnitude of AB. So if I did that, I would be left with my unit vector between P1 and P2 is the distance xi plus distance yj plus distance zk, normalized by the total distance between those 2 points, which is the square root of the sum of the squares of the components. Okay, and this was the alternate way that we sort of defined our unit vector of a force between 2 known points. Okay, so here's our unit vector. Then we know that our force is whatever the magnitude of that force is, multiplied by that unit vector. And that's pretty much all the information that we had gone through material-wise for this course. We had seen a bunch of different types of problems where we're utilizing this information in a variety of kind of like unique ways. So in 3 dimensions, maybe you got like 3 ropes that are holding up a flower pot, or sort of these 3 cables that are suspending a traffic cone or traffic light. I think that was one of your homework problems that you saw. But they're all basically revolving around this general idea, is that you have to create or somehow express the force in its rectangular components, I, j, and k, because that allows you to utilize it in this 3D particle equilibrium, which is kind of the problems that we were analyzing. So we have tools to get to this point, and we now, to sort of cap off the problem, or cap off the course, utilize this tool for 3D equilibrium. Specifically of a particle. It's basically the same as 2D. Sum of the forces equal to 0, which led us to sum of the forces in x equals 0, sum of the forces in y equals 0, and sum of the forces in z equals 0. Okay. And so for our analysis, being able to describe the force in its rectangular components by creating this unit vector lambda, which expresses that force in its various principal directions, I, j, and k, becomes important when we're looking at using these particular equilibrium equations. So if we're enforcing sum of the force x equal to 0, sum of the force y equals 0, sum of the force z equals 0, we have to be able to resolve whatever forces that we have on our particular particle into those directions so that we can do math appropriately on those particular guys. All right. So we saw a variety of different problems. You got a lot of practice problems doing this and seeing this in practice. So hopefully you take a crack at those practice problems that I laid out for you online. A lot of you asked for it in your first homework and kind of like those bonus questions. So done that for you. I have handwritten solutions for all those. I encourage you to take this time right now, go through some of those practice problems, especially stuff that you're shaky on, give them a go. And we'll see you then tonight for the review session. So look forward to seeing you tonight at 7. That's it for today. We'll see you then.